Okay, we um, we are looking at the Patran screen after we have initiated the program from the programs menu and click on the appropriate icon for a Patran with MD Nastran enabled. So in here we need to create a new database. So we go to File and we say New, and then seeing here we go and say this, we're going to call it simple, and call it for a simple supported beam. So this is going to be different than what we did in the prior example. We're going to change the boundary conditions, or either we could also fix the nodes, but or we could make it simple supported beam. So in this case, we'll say OK, and now we need to start. You see, you have in here we have several things that we should on the very beginning on the first screen to check what kind of solution we're doing. Like in this case, you see analysis code. In Patran, you have several analysis codes. You could Patran could actually work with all these other programs, with Dytran, with Cinda, with Abacus, with ANSYS, you name it. It's got many. In our case, we just want to do with MD Nastran. And these are the kind of solutions that we have. It is a structural solution that we need. So what I'm going to do is to observe these tabs in here. Geometry, properties, this would be to draw the part that we need or what we are analyzing. The properties would tell us whether the elements are uniform or the elements are different, whether they are made of different material. And of course in here we also put the material properties. But in here the loads and boundary conditions. Nastran has the ability to analyze several problems on the same model. So for that reason, you need to define the loads, boundary conditions, and the properties in sets with their own names. So in here we go and set up we fix the nodes and we put the loads. Meshing is to divide the geometry in finite elements. I like to go from geometry to meshing and then do these other things on the finite element model itself. Then the analysis has to do with the generation of the matrices and sending it to the analysis code, which in this case is Nastran. And then we submit this to the job, optimizes the matrix inversion and calculates the nodal values. And after this, we would have to go on this same part to a place where it says access results. See, we access the results, and then we look at the results so we can plot them the way we would like. Okay, so let's just do a simple example as we have we call it simple supported beam, and then we're going to go here to the geometry. In this case, I need to create the way we did it. We did surface from curves, and we did the curves from points. So if I pick this, you can see this. You see this option on the screen. This one allows me to put the screen position. So if I go and do a click here, do you see it made a point in here? And then do click here, it made a line. And then if I click another one in here, and then we go over here, then we have made another line. Now we can create a surface with two lines. So create, and now I'm going to do surface, two curves. So I need to do, all I need to do is click on the first, click on the second, and I got my surface. Everything okay? So we basically, for this particular example, we have finished the geometry, because what we are doing is we are analyzing a simple supported beam, looking it from its side. So in and out of the screen you have the thickness of this, so you have the surface over here. So the next thing we're going to do is go to the meshing part, and for this I am going to say see mesh seeding here, and then we have by default 2. So if you click on a side, it's going to create 3 nodes, 2 elements. Click on the other side, it's going to create 3 nodes, 2 elements. I mean, on the side. Over here, I would like to do more, so I'm just going to put 8 per side. Click on this line, and look, I got my 8 elements, 9 nodes. See, 1, 2, 3, 5, 6, 7, 8, 9. And now we have this one. Yeah. Now here comes a crucial step, because now we are in a position to create a mesh. We did the seeding, meaning we specify on the sides what we would like to have, and then we let the computer figure out the rest. How is it going to divide it? I personally believe that it is better to do a symmetrical area, I mean, at least as we're beginning, because I could have specified on the bottom more elements than on the top. And if I did do that, the computer is going to have to reduce the number of elements and nodes on one side than the other. So in this case, it's uniform. So we need to make sure that we go now to mesh, and here's where we need to make a decision. Do we want quad elements or do we want triangular elements? I did one example with triangular elements, so just to be different or make it more interesting, we could do quad elements. If you click on the select let's see, there we go. We click on the surface and we click on apply. Look what happened. It created quad elements right now. We can do it with triangular elements, and the last example I worked with triangular elements for the very reason that we had actually looked at the theory of triangular elements. We haven't done much with quads, but from the point of view of the computer program, really doesn't make too much difference. Okay, so I am going to I'm going to keep the quad elements for now. What we need to do, and here's something that you need to keep in your mind, is that the loads and the constraints that you want to put on this surface and on this model have to be done at the nodes. If you don't do that and you keep it on the geometry, you have taken a path that may not lead you to an easy solution, because there's an option. I mean, people use it that way too, but I believe that it's better to make things a lot easier. So I did finish doing my mesh. So I'm just going to go and put the loads and boundary conditions, and in this case the displacement is the first conditions. So I'm going to give it a set. Remember what I was saying about this idea of sets is because you could actually use the same model to analyze it with many different loading conditions. So this set for displacement, I'm just going to call it displacements. How is that? Yeah. Just give it a name to this, and then I need to put the input data. Here is the trick. If we are going to do simple supported beam, isn't it true that it is free to move in the x direction, would move on the z direction, but not on the y, right? So I think that what we need to do is to make sure that there's no motion on the y. So we need to specify that. We could do it this way. We could say it occurs to me we could do it like this. See, 1, 0, 1 is like a vector that indicates that on the y direction there is no motion. And in here I'm just going to say 0, space 0, 0, no rotations. So if I click on OK, and then I click to select the application region, here is a problem. You see up here, when you're going to select the application, if you click on geometry, it's just going to put on the whole surface, ignoring the finite elements. I do not like that. I want to do finite element model entities. So in this case, select the nodes, it says. I'm just going to select this too. See, select the nodes. And then maybe I'm just going to add to these ones and select this too. Yeah. So if you click on add, we have those 4, and click on OK. And then I click on apply. It should do my boundary conditions. You see what I mean? All right. Now I need to do the loads. I need to do the loads and boundary conditions. They are grouped in the same. So this is going to be a force in here. Now we're going to do a force, and in this case the set name, we're going to call it force. Yeah. And then in here we go input data. The force is going to be in the minus y direction. So in here we have 0, and then minus 1000, and then 0. And then we have to say moments are on each node, no moments. And after I have done that, I click on OK, and I need to, we did the input data, select the application region, yeah, and in this case, how about if I load this beam over here, select these 3 nodes, click OK, click apply. Yeah, and I have my loads now. So keep in mind what we have done. The constraints have specify what those nodes do. and the loads also have specified what the nodes do. So at this point we have finished our mission of dividing the area of the part in finite elements. We pick quad elements in this case, and now we have finished just a moment ago putting the loads and boundary conditions. That's loads and boundary conditions. We chose two nodes for the boundary conditions for the displacement each side, and then we chose three nodes on the center of the beam. So that's where we are. Now we need to tell the computer what this beam is made of. If we don't tell it what material is made of, how is it going to know? I think it's not going to be able to do it. So what we need to do is to specify the materials. So we have done the meshing, we have done the loads and boundary conditions. Now we need the properties. The first thing we gotta do is to define the element properties and their shells and so on. First of all, we need to create a material. See, isotropic material. Create isotropic. Call it. What is the material name? I'm gonna call it like I did last time. Steel. Yeah, it's made of a steel. We put the input properties of this material. As this is logic, this would be 13E6, like that. Poisson ratio 0.25, and okay. So we did the material properties, but you see, there is a big difference between the material properties and the element properties. Please make sure that you keep that difference in your mind. The material properties are the modulus of elasticity, whatever we just entered, or the materials that we are using for this beam, or if it's made of the same material or composite, then that's when we have different modulus of elasticity, and therefore we would need to enter specifications for both materials. In this case, it's an isotropic material, as we are defining it here. We put the input parameters, modulo of the elasticity, Poisson ratio. We could do this damping and so on, but we don't have information on this problem to do it. So in here you go, okay, change the material status. So I think we have entered the material name, the properties. Now we need we really need the element properties, because we need to select the application region also. If you click on apply for this, yeah, we have done the material. But now we need to select the properties. See, two-dimensional properties. And here we go and put the property name. Let's call it property 1 to indicate that we could have different properties. Input properties. You see here, we clicking here, say steel, pick that up. And then thickness, I would say 2. Just to get something. Okay, so we got the thickness and we have the material properties and we have what it's made of. So it's important now to select the application region and to do that because this is an isotropic material. I'm going to do it this way and then I'm going to say okay, and then you click on apply. Okay, so we did the material properties, we did the application region to the whole thing, and now we're ready to go. We're ready to go to the analysis in here. We have already chosen full run, and in this case we need to do a subcase. I think these other things are to indicate what solution we would like for example this one. See, you can specify several solutions. We're not interested, we're interested in the linear static one. So we have, let's see, we have in here this, we're in the solution in here, the analysis part. Yeah. So at this point we have the we are ready to send this to Nastran, and we need to define the subcase. Let's call it case 1. So that's the subcase. I mean that's the subcase. And I'm going to select that one and I click on apply and then click OK, yes, click cancel, and in here I am going to go and do the submit for analysis. So I need to submit this to be analyzed and full run. You see subcase select, we did that, we click on apply and the computer is going to go to work. You see in there, it's going to go and do the Nastran beginning job, and the processes are logged in there, and it did the result. So I need to actually select the result, the results file. Like in here is the analyze. You say access results, and if you access results on over here, no, here, select input file. So I need to make sure that this results file is here. If it isn't, then see there it is, simple supported beam, and we say okay, apply, and so the computer attached the file to the program, and so we have access results. So we have done all this stuff. We have finished the calculations. We did the access results, and so now on the results file I am going to look like forces transitional, and if you click on apply, this is what you will see. You click on the displacement translation, maybe a little better, or if you click on the principle, well, let's see, I would say this is the translational one, would be so simulated like simple supported beam on this end produces this kind of stress. But what I am interested is is to calculate the deflection. Displacement translational. Let's see what happens. We can examine all this. Constraint forces, apply. Then we have displacement, rotational displacements. Then translational display says principal stress direction. Okay, so you click on apply, and so it actually did two of these, and apply. Let's see in the principal stress, the deflection, or these are the constraint forces, the translational forces, displacement rotation, principal stress direction, zero shear. Okay, there we go. So you could animate this thing, but you could also animate the deflection, not just the results. So animation control, we have results. You could examine all this stress invariance, apply. No, we didn't want the animation, but it's doing it anyway. Results, we don't want to animate anymore. Principal stress, zero shear. Stress tensor. Yeah. But I think the idea is to be able to get to this point, the results. Post animation, we don't want to do it anymore. Okay, so we go to the results. I think I'm just going to leave you with one of the results files that may look a little more interesting. These are the rotational ones, translational displacements, principal stress, So we have in here, you see this beam, the way I put the constraints, it actually made it move to the right by putting that one, but we put all zeros, then it would constrain all of them. But this is why the results are probably a little different than I would want to see. So here we go. There you go. This is the stress, and it makes sense that it's higher over there. You know, the loads is just on one in here and on this too. So this makes sense.